Every star you've ever seen is dying. Every galaxy is cooling. The universe is running out of usable energy, and it can never come back. This isn't philosophy or science fiction. It's a mathematical certainty derived from one of the most ironclad laws in physics. By the end of this video, you'll know exactly when the universe will die, why it has to, and the wild theory some physicists have for cheating it. Last video, we proved cold doesn't exist, heat is just atomic motion, and motion always spreads out. Today we're going to take that idea to its terrifying conclusion. Because if heat always spreads, and the universe is one giant system, what happens when there's nothing left to spread? That's called the heat death, and the math behind it is beautiful and a little bit horrifying. Quick recap. Heat is the kinetic energy of atoms. Hot means fast, cold means slow. And there's a law called the second law of thermodynamics that says the entropy of the universe, the disorder, the mixed-upness, only ever increases. It never decreases. Ever. Drop ink in water, it spreads. It doesn't spread. Drop hot coffee in cold milk, you get warm, you don't get hot and cold back. The universe has a direction, and that direction is more mixed. This isn't just an observation. It's statistical. Take a box with hot atoms on one side and cold atoms on the other. There's exactly one way to arrange them like that. But there are trillions of ways to arrange them mixed up. So as the atoms bounce around randomly, they're overwhelmingly more likely to end up in a mixed state, just by sheer probability. Entropy increases not because the universe wants it to, but because the math has no other option. Now zoom out. Way out. Treat the entire universe as one closed system. What do we have? We have gradients. We have hot stars surrounded by cold space. We have spinning galaxies and stationary dust clouds. We have nuclei fusing in stellar cores at 15 million Kelvin, and microwave background radiation at 2.7 Kelvin floating in the void between galaxies. These differences are what make anything happen. Stars shine because they're hotter than space. Life on Earth exists because the sun pumps high-energy photons at us, which we use, then radiate back out as low-energy infrared. We're not using energy, we're using the gradient between hot and cold. This is the key insight. You can't extract work from energy unless there's a difference in temperature. A river only spins a turbine because water falls from high to low. A heat engine only runs because heat flows from hot to cold. If everything in the universe ends up at the same temperature, even a warm temperature, nothing can happen. No work. No motion. No life. No thought. Energy still exists, but it's useless. That state is called thermodynamic equilibrium. And it's where the universe is heading. In 1824, a French engineer named Sadi Carnot derived the most depressing equation in physics. He was studying steam engines, but he accidentally figured out the universe. The maximum efficiency of any heat engine, including stars, including life, is 1 minus the cold temperature divided by the hot temperature. If your hot side is 1000 Kelvin and your cold side is 300 Kelvin, your maximum efficiency is 70%. If they're both 500 Kelvin, your efficiency is 0. You can't do anything. The energy is still there, but it's useless. Carnot's equation is the universe's report card. And as the temperature gradient shrinks, the universe's ability to do anything shrinks with it. In 1877, Ludwig Boltzmann gave entropy its full mathematical form. Entropy equals Boltzmann's constant times the natural log of W, where W is the number of possible microscopic arrangements. This equation is so important they engraved it on his tombstone. It says entropy isn't a vague idea, it's literally a count. And the universe always evolves toward states with the highest count. The state with the highest possible count? Maximum mixing. Maximum sameness. Heat death. Here's the actual timeline. We're currently in what cosmologists call the stellar era. Stars are forming, burning, dying. This is the loud, bright, energetic phase. It's also temporary. In about 100 trillion years, the last star will run out of hydrogen. The smallest red dwarfs will be the final ones, they burn slowly. After that, no new stars can form, because all the gas needed to make them will be locked up in stellar corpses. After the stars die, we enter the degenerate era. The universe is dark, lit only by the dim glow of white dwarfs, the cooling cores of dead stars, neutron stars, and black holes. Even atoms start breaking down. Protons themselves may decay over timescales of 10 to the 34 power years, that's a 1 followed by 34 zeros. By the end of this era, ordinary matter as we know it is gone. Just black holes left in an empty sky. Now even black holes start to die. Stephen Hawking proved in 1974 that black holes slowly leak radiation, Hawking radiation, and eventually evaporate completely. The biggest ones take a long time. A supermassive black hole with the mass of a galaxy takes about 10 to the 100 power years to evaporate. That's a googol of years. To put that in perspective, the universe is currently 1.4 times 10 to the 10 years old. We're in the first trillionth of a percent of cosmic history. Once the last black hole evaporates, we enter the dark era. All that remains is a thin soup of photons, neutrinos, and stray particles, all at almost but not quite absolute zero. No structures. No gradients. No motion that can drive any process. The universe still exists. But it can never do anything again. Forever. Now, physicists are stubborn. Some have proposed wild ways out. One idea, Boltzmann brains. Given infinite time, even at near equilibrium, random fluctuations could spontaneously assemble, including, theoretically, a fully formed brain with false memories. Statistically, in an infinite lifespan universe, more conscious experiences would come from these fluctuations than from biological brains. Another idea, vacuum decay. If our universe's vacuum isn't truly stable, a bubble of true vacuum could nucleate somewhere and expand at the speed of light, rewriting physics. Bad news short-term, instant annihilation. Good news long-term, new universe, new gradients, new possibilities. A third, cyclic universes. Maybe the heat death isn't the end. Maybe the universe contracts, bounces, and starts over. We don't have evidence, but the math doesn't forbid it. Here's what I find beautiful about all this. The heat death isn't an apocalypse. It's not a war or a disaster. It's just bookkeeping. The universe doesn't die, it equalizes. Every difference smooths out. Every gradient flattens. The energy is still there, perfectly conserved. It's just spread out until nothing can use it. And that means every star, every galaxy, every gradient is a temporary, statistically improbable knot of low entropy in an ocean trending toward sameness. The universe is doing something interesting right now, because it isn't at equilibrium yet. The dance is still happening. Remember the candle from the first video? We said fire is a verb, a process of atoms rearranging and releasing photons. The universe is the same thing, just bigger. A 13.8 billion-year-old flame, slowly going out. It'll outlast every star that will ever form. But eventually, inevitably, the math wins. The atoms slow. The light fades. And entropy reaches its maximum. That's the heat death of the universe. If you watched all three of these, fire, heat, and heat death, you've now seen physics scale up from a candle to the cosmos. That's the playlist. Subscribe for more videos that start small and end big. Comment entropy if you made it this far.